Thank you, Mateusz. Thank you for sticking to the bitter end, and thank you, organizers, for inviting me. This is really a great pleasure to be here. I must say, I think this is the best organized conference I have ever attended, which is not a small feat. I'm really happy to be here. I originally graduated from Warsaw University. I must say that actually I'm stressed because I don't think that I have ever given a lecture like that in Warsaw. And what I will tell you about today is essentially how accurate one can make Green's function methods, and let me just tell you why I'm talking about it. So in my group, we basically develop post-DFT methods for molecules and solids, but in solids, many of these post-DFT methods, which are fully ab initio, right, for fully realistic system, they, I would say, forefront enough that there are many groups, there are many results, they not always agree. And I think there is a genuine discussion how, how this can be implemented, how this can be cheap, and how one can make these methods better. So what I will tell you today is about one particular method, GW, and about many misconceptions that are present in the field, even though the method is widely used. So I will basically, how we're going to go about it, I will tell you what GW is in the kind of easy terms. And then we will talk about different self-consistency schemes in GW, about relativistic GW, and finally how energetics can be evaluated in these methods, how one can improve them, and how one can make them cost-effective. And because this, this conference is actually about high accuracy calculations, right, for intermolecular forces, as some sort of small bonus, I will try to squeeze the most accuracy out of it so we can evaluate, if it can be used also in these regimes and for what kind of large systems. All right, so at the beginning, right, one can ask, why do we need Green's functions at all? Like, after all, most people in this community use wave functions, right, or DFT. So why do we need Green's functions? So imagine that, for example, one wants to study solid, like this is the chromium, sulfur, bromide, van der Waals crystal. So it's actually a layered material that my colleagues are synthesizing. And this is like two spin lattices that are interacting. So they usually want to learn something about this material. So they use angle resolved photoelectron spectroscopy, right? So in this experiment, they cleave this crystal, any crystal, and then they have a photon source, right, that is incident on this sample. This photon source is ejecting electrons, usually from basically the surface and slightly below the surface. The electrons are caught in this collimator, and they measure basically the energy and momenta of these electrons, right, and they learn about the basically orbital bands in the solid. So what they are measuring is in theory, right, called basically spectral function times some sort of matrix cross-section element, so we will not worry about that, but what they are measuring is the spectral function, which you can say that basically depends on Green's function, right? So as long as we can evaluate this Green's function, we can actually describe very well a series of experiments in solids. So, right, so this description of Green's function is our goal. So usually, these experimentalists, they tell you that they have very well resolved results, and they give you something like this, and they say, tell me what this band is. So when we do this, right, and we tell them that this band, for example, comes from, I don't know, D electrons or P electrons or some kind of hybridized electrons, right? So they also change during this experiment the momenta, right? So we have to basically have the full momentum resolution for the solid, and you can recognize that these are basically different cuts through the band structure, right, which is much more basically common, right, to see this type of spaghetti diagrams. So as theorists, we need to evaluate this correlated Green's function. So you can see that in this correlated Green's function, right, there is a part that is Fock matrix and a part that is called self-energy, basically. So the self-energy will describe all many-body effects that are present in the solid. So basically our goal, right, is then to illustrate this part, which is called self-energy, which basically tells you how electrons interact to our best ability. So, right, so we have basically several axes in which we have to make this self-energy accurate. So we describe correlation, right? So we can describe it at different Green's function levels. So the lower level are the GW or GF2 methods. Then we can, and this can be described at what we call weakly correlated systems or strongly correlated systems. Then we can also describe relativity, right? And we can have basically usually two-component approaches with these methods. We can include temperature, which we do. So it's basically gives you something like summation over many states in order to be able to express how basically the material changes when temperature is applied, right? And finally, one has to converge it with the basis and, God forbid, describe disorder, which, is non-trivial. We don't do this. All right, so these are the challenges, right? What we usually do, we describe this weak and strong correlation, temperature and relativity. We obviously converge everything with the basis set. So see, the simplest, right, of this post-ab-initio Green's or the simplest ab-initio Green's function is just Hartree-Fock Green's function. But that would give you basically a spectrum, right, which is just a series of peaks. So obviously we want better, right? So we want to add this self-energy, which will describe the many body effects. And then you're going to get the spectrum, which is, right, naturally broad and due to all these interactions between the electrons. So the self-energy, which we describe, can be expressed as a series, right? So it's described as a series where Green's function is multiplied by a term called W. And then, right, higher order terms. So this W describes basically what we call Screen-Coulomb interaction, right? So it describes how an electron moves through solids. So imagine that basically like a single electron moving through solids undisturbed in Hartree-Fock, right? If you think like a particle is a horse, moves undisturbed through everything. But in correlated approach, right, it drags all the other electrons around like a horse would drag a cloud of dust, right? So we call this quasi-particles. And basically, right, the simplest approximation to the self-energy would be the first term of this GW expansion, so just G times W. All right, so you can see, right, that this self-energy depends on the Green's function. So immediately you can observe that there is some sort of self-consistent cycle involved, right? So we evaluate self-energy that depends on Green's function. When we evaluate Green's function, we can evaluate the self-energy again, right? And we can iterate till convergence. So this self-energy, right, for like aficionados of diagrams is given as just sum of bubble diagrams, infinite sum. But computationally, right, it basically one can write this as such term. So you can, even if you don't want to look what the indices are, let me tell you that this is actually quite expensive, right? Because you have summation over grid that describes the spectrum of the Hamiltonian. You have basically number of momenta that you have to cover in solids, right, and orbitals. And that scales as, like if one does this everything very accurately without any approximation, that would scale as n to the sixth, right? So this scale is basically like a CCSD, so quite expensive. One would not be able to do it this way for solids. So one has to basically introduce some kind of approximations. And see, these approximations, right, in evaluating this expression leads to many of these misconceptions or disagreements, because basically, right, there is no single way people introduce this approximation. Everybody has their own preferred way, not always described actually. And that leads to basically multiple computational protocols, right, that one performs in this post-DFT calculations for solids, usually due to expense. One has multiple bases, right, because one can use plane waves, Gaussian orbitals. So that means that these implementations not always agree with each other. And then, on top of that, people introduce other types of approximation, usually that deal with truncation of the self-energy series. And right, like you could see the experimental data. The experimental data are also not great in this field, right? So that means that even if you do these approximations, you're not always penalized because maybe the experiment is not accurate enough. Or, if you do it accurately, it's actually hard to see sometimes that you're accurate because you cannot necessarily agree with the experiment. So there are many implementations, right? And if you wanted to run some of these low-level Green's function methods, there are very many codes, right? Like, for example, the most known would be Berkeley GW, Quantum Espresso, or VASP. You can run these codes there. They have severe approximations. And we will discuss basically these common misconceptions and, how one can overcome this. All right, so in my group, we work with Gaussian orbitals, actually, in this Green's function implementations. So why do we do it? So the good thing is that one has like an excellent compact representation of the orbital. So that allows us also to have chemical meaning for the orbital. So if the experimentalists come to us, we can, very easily interpret without any linearization or any procedures which itself, sometimes rely on some approximation. And it also allows us to have the common machinery between molecular and basically solid calculations. The cons is that it's not easy to converge to the basis set limit. Like these Gaussian orbitals can get very linearly dependent in solids, and actually they are very undeveloped. So like if you wanted to do the calculation for, let's say, nickel oxide and wanted to have a basis set in Gaussian orbitals optimized for solids, you have 5 basis sets. If you want to do the same for molecules, right, and you will check how many basis sets were optimized for molecules, you have 200 basis sets, right? So this is basically like the field is rife with challenges. So what one can do sometimes, if one basically faces many of these bases that are not optimized for solids, one can do material-specific optimization of a basis set. And look, this is a plane wave result for nickel oxide. This is a result of LDA in a basis that is basically claims to be optimized for solid, but you can see that basically doesn't give right result, right? One can material-specific optimize the basis and basically recover the right results. So we sometimes have to do it in order, to ensure that there will be like a very good match with experiment. So there is other right challenge in all of this, that it's so costly. So how one can overcome that? So basically what we do, we use the density fitting of two-body integrals, right? So what that means is that we split this 4-leg tensor into 2 tensors that basically have, right, only 2 legs, orbital legs. So that reduces the cost, right? So then the cost is like n to the 4th, so it's much cheaper. So one can actually perform this, decently on a solid. And in addition, we also have to deal with this grid, right, which spans the spectrum of the Hamiltonian. So over the years, we actually worked for a long time on this in order to control this accuracy of a grid, because usually in many of the codes, it's completely uncontrolled. And then we use this grid, which is called intermediate representation grid, developed by us and our coworkers. And you can see that indeed one can converge basically past 6 digits, actually until 12 digits with these results with the grid. So energy can be converged very well. All right. So let me tell you, like the first one of the misconceptions in this field is that there are very many self-consistency schemes that people perform. And for years, they usually argued that the cheapest self-consistency schemes are the best. And the expensive ones were simply not performed, but argued that they are not good, right? So we actually checked this, and let me just show you how, how kind of large the zoo of things is, right? So one can perform this GW on real axis, and then one can have plasmon pole approximation, so one can have only one frequency. So this is what Berkeley GW does, or one can have multiple frequencies. And then at the end, one does the quasi-particle approximation, which basically amounts to calculating only the diagonal elements of self-energy. So this is, kind of uncontrolled, right? You check out all the off-diagonal elements and you count that this is good. So this one I would say is mostly historical, but this sort of quasi-particle approximations, these are very commonly used when one does G0W0 based on various functionals, right, or quasi-particle GW. When we do this on imaginary axis, because we have finite temperature, so we can basically increase the temperature of our solid, we have multiple frequencies, we fully iterated, and we have the full self-energy, but since it's obtained on this imaginary axis, we continue to real axis to obtain spectra. And basically this gives a method that is independent of the starting point. We don't rely on the starting point the same way the G0W0 methods rely. So basically if you want to remember something, there are two flavors of the zoo, right? That there is a quasi-particle approximation, which only gives the basically diagonal elements of self-energy, or one can use all elements, but then one has to continue. So what we do is basically we do fully self-consistent GW that is implemented in Gaussian orbital, right, that provides all elements, doesn't have any truncations. And then, right, the misconception is that this partial self-consistency are good, the full self-consistency is not. So there are many flavors, right? So in the full self-consistency, we basically compute Green's function, compute self-energy, and we solve till the iterations converge. In this partial self-consistency, usually one computes Green's function, computes self-energy, even one finds from that better DFT functional, reevaluates fog matrix, and this is the iteration that one performs. So it's kind of like actually a cook-up, but the hope is that one can perform fewer iterations. So there are many, again, the schemes fall into Shilfgard-Kotani scheme or Kutepov-Howle scheme. And that, you know, like usually if you run VASP, for example, this is what we run under GW. So the pros is that seemingly the scheme is cheaper, or it's said to be cheaper. The cons that one cannot converge energy, it converges slowly. In this full scheme, actually energy is well defined, one can converge everything tightly and one can reach the convergence. So how does it work on simple systems like semiconductors? So you can see that PV gives actually quite an error in comparison to experimental bandgap, right? So that's known result. The G0W0, they say it's very good when one has this on PB reference. So for some of them, it's good. Yes, it indeed agrees with experiment. But if you take a little bit more complicated system, you see that it actually is unpredictable, right? Because it kind of here gives results which are far off. And then all this, right? All the partial self-consistencies, they all give actually very similar values. So there is no reason to say that the full self-consistency is bad. All the self-consistencies predict very similar bandgap. But if you look at the convergence characteristic, the full self-consistency can be converged very nicely to a high threshold. And these partial self-consistencies, right, they basically either cannot converge at all, or they give up at a low convergence, right? So they actually do have problems. So they are poorly convergent. And when one, you know, so this was for solids. So for solids, at least one can get some result from this partial self-consistency. But for molecules, like if you take basically like a data set for 29 molecules, which is commonly analyzed in the community, and you can see that this fully self-consistent GW has basically the best mean average error and standard deviation, both with experiment and with respect to CCSD, from all these other self-consistency schemes. So I would say, so that's one misconception that we were able to consistently, I think, explain, partially also because nobody ever implemented the fully self-consistent GW to a good accuracy, and never the schemes were investigated in the single basis, right? For example, some of them were in plane waves, some of them were in Gaussians. So we also have the relativistic GW, which we developed over the years, right? So we're going to move on to this axis. And basically, we don't use 4-component approach because it's too expensive, right? That would mean that we have to re-evaluate all the Coulomb integrals. So that's basically expensive, and it would be difficult for us to build embedding on top of this. So what we use is the two-component approach, because this one is basically very easy for us to build some embedding with higher level method on top. And then basically our one-body Hamiltonian, or Fock matrix in this theory comes from basically two-component transformation, of the non-interacting four-component Hamiltonian. So the Hamiltonian looks in the simple form that we have this full relativistic one-body Hamiltonian, but non-relativistic Coulomb integrals, which can be easily evaluated. And this type of Hamiltonian can be easily used in this basically ab initio post-DFT methods. So if you look right now at the solids, like for example, silver bromide, so this is the non-relativistic results. You can see that basically the first level of the relativistic result is called spin-free. So that does not yet illustrate spin-orbit coupling. You can see that basically this unoccupied band goes down, So it changes the band gap. And if you do the fully relativistic calculation that illustrates spin-orbit coupling, you can see that basically you start to develop this spin-orbit splitting, due to relativity. That can be evaluated actually quite well in this theory. One can converge, these spin-orbit splittings with the basis set, and one can converge everything with finite size effects. So this is a very controlled calculation that one can actually get a very decent accuracy. So I would say we try to demolish this claim that, this is only inaccurate because the experiments are inaccurate, So one does not need to do any better. So can one get accurate energetics from this method? So basically the common misconception is that from this G0W0, or from GW, you cannot get energy. Many times people will tell you this is not a total energy method, you cannot evaluate it. So how accurate one can make these energies? So see, when one does the full self-consistency, everything is basically theoretically well justified and what we call thermodynamically consistent. So what that means is that no matter how you evaluate the energy, it will give you the same value. And that's actually non-trivial because you can evaluate the energy through regular Green's function expressions called Galicki-Migdal, or you can do it by thermodynamic integration. And they indeed give the same values. So that is good, Because it means your results are unbiased in any way. So right now, we can basically start comparing the energetics. So what we do, we usually evaluate the bulk moduli of solids, for example. So in the bulk modulus, you have this uniform, basically pressure squeeze. So you not only have to describe the minimum well, but also the whole curvature of the curve well. So that's actually non-trivial, This is as for diatomic, you need to describe the full curve well. And there are many questions, if this can be done accurately. Can we describe all these regions? Can we describe basically the repulsive wall, how it compares against DFT? So DFT is commonly believed, to work, for example, very well for the semiconductors. But even in the lattice constant, if you compare, for example, for silicon, cannot get any easier than that, PBE, with experiment, you can see that actually this fully self-consistent GW does better. Okay? So this is a very small point. One shouldn't get excited about that yet, but look at the bulk modulus, This one is actually quite underestimated. And from fully self-consistent GW, with basically relativistic correction included, one can really get quite close to experiment. And this gets, only better, if you go to heavier, basically solids like germanium, You can see that, again, DFT gives bulk modulus, which is heavily underestimated. And basically from GW, you can start getting, results that are much closer to experiments. So this is alpha tin, which is apparently judged to be topological material that we calculated for our collaborators. And you can again see that actually one can get very good agreement, And DFT can get quite poor actually agreement in comparison to experiment. All right. So basically one can get very good accuracy, right, and good energetics. So what are the dangers? So if you look here, right, this is a series of basically solids, right, which are gallium arsenide, the zinc sulfide, right, and you can see that basically these are the errors in bulk modulus. From DFT, one gets consistent errors. If you look at these curves, not the pink curve, but the other curves, one can get actually good results from GW with all electron bases, but with pseudopotentials, one doesn't get good values always, because the pseudopotentials most of the times were constructed for DFT calculations, and we see that actually when we start to be highly accurate, that they don't recover such good values. So another challenge is that in many of these experiments, even though we can include relativistic, for example, in this GW, right, if the experimentalist will give us this, right, we may not always even see, for example, the splitting to spin orbit, even though we are able to illustrate it at the level of theory. So the challenge is that basically one would need to construct better pseudopotentials, right, and not always the very sufficient experimental comparison. So let me tell you about one more quantity that basically proves that actually these methods are quite accurate. So we can evaluate Néel temperature. So see, Néel temperature is like a transition temperature, right? That below Néel temperature, the solid is magnetically ordered, right? Like for example, it's antiferromagnetic. And above Néel temperature, it becomes basically, the spins become randomly disordered. Right, so this is like a transition temperature. This is actually very non-trivial to calculate fully ab initio in a solid. So these are series of nickel oxide, cobalt oxide, and iron oxide at Néel temperatures. So see, these are experimental temperatures. We actually have high deviations between these experiments, mostly due to impurities. If one does this at the level of DFT, we cite here Hartree-Fock, but DFT looks the same. See, the regular trend is nickel oxide has higher Néel temperature than cobalt oxide, and cobalt oxide higher than iron oxide, right? And at the level of this UHF, you can see basically that nickel oxide indeed has higher Néel temperature, but cobalt oxide is comparable to iron oxide. So it doesn't distinguish between them. If we do GW, we recover the experimental trend correctly. Right, so basically nickel oxide is higher than cobalt oxide than iron oxide. And we know that this result is quite accurate because for nickel oxide, one can basically predict this temperature based on finite size clusters. And DDCI, right, which is just some sort of active space CAS with double excitations outside, gives comparable actually result as GW. So how this is done, right? We basically do the GW on the whole solid. We get from that basically like a spin Hamiltonian. So we get J1 and J2 coupling constant. Based on that, we do finite temperature expansion where we actually calculate temperature-dependent magnetic susceptibility, and where it has basically like a kink, which signifies phase transition, we read off the temperatures, okay? So SCGW can give good accuracy, right? Can give energetics, can also give this J1 and J2 coupling constant, both for solids and molecular magnets. So then there is also one more kind of issue, right, that people have in this community, that they say that adding vertex to this GW is what's going to make it more accurate. So that means, right, that instead of having the first term here, we start to add all these higher order terms, which are called vertex. So there are many theoretical questions, like what is the best way actually to add the vertex? Does it improve the results, right, and how to make it cheap? And because normally it would be terribly expensive. And there are many papers with many claims, like for example, see, these are the quasi-particle excitations of various molecular systems, and people say that some of them can be this, what is called SQP, single quasi-particle region, can be described well with GW, But these multi-particle excitations cannot be described well with traditional GW only when vertex is added, basically, right? That vertex is necessary to describe this part. So we put it to the test when one does everything fully self-consistently, not at the level of the GW0. And you can see basically that these are the vertex result, right? These red bars. They are done in comparison to basically selected CI results for this molecular system, so different IP peaks. You can see actually that the vertex, it is very bad results when it's done on this G0W0 level, right? And fully self-consistent GW gives better results comparable to EOM CCSD. So actually, this vertex at top of G0W0 with all approximation is not a good method. And you can see this here. This is G0W0 and the mean average error, right? You add vertex on top of PBE, great, on top of Hartree-Fock, terrible, right? So clearly, basically this is, one can of course manipulate this reference, but this is not what theorists would want to do when one does fully self-consistent GW. It's consistently better than this column without any reference dependent. So we investigated this, and my student could see that the vertex always moves the results to the right, so the game is only to find appropriate reference, and then one can hit the good point, but that's not what one would appreciate, right? And this one depends very strongly on the functional. So how to make it cheap, right? Like one can believe many times in this community, one believes that one has to introduce many approximations which are uncontrolled to make this method cheap. So is this the case? So we basically use the THC, which is tensor hypercontracted decomposition with Miguel Morales from Flatiron, who is our coworker, and Qianan Ye, who was my former student. And then the whole method starts to scale after this tensor hypercontraction as n cubed, right? Times this n tau, but this n tau can be made embarrassingly parallel. So that starts to be almost as cheap as DFT, I would say. And this is actually accurate enough. We can converge this decomposition accurately enough to evaluate interaction energies. So Pavel actually, who is my postdoc, did this amazing work, and he calculated this S22 benchmark for intermolecular interactions with GW. Doesn't work that well, but nevertheless, he still was able to converge, right, to such accuracy to use supermolecular method to evaluate energies. And you can see this is the SCGW curve. These are the RPA curve. They depend on the reference. When one does add the vertex, but on fully self-consistent GW, one basically gets in this regime. So accurate enough, right, to calculate, can be converged accurately enough to evaluate interaction energies. So what did I tell you? I told you about all these different self-consistency schemes, that they give several band gaps, that they are similarly costly, and the energy is only well-defined in this fully self-consistent GW, not in any other schemes that people let you believe. That in the relativistic GW, one can get very highly accurate energies, but sometimes problems appears with basically when one doesn't do relativity, but one only uses pseudopotentials. That this GW plus vertex result, most of the time in the community, when they use with G0W0, they're not accurate, and then one should do full self-consistency in order to improve it, and one can make GW as cheap as DFT without any uncontrolled approximation, but when one uses controlled decomposition of integrals. All right, so I would like to thank people who did the work. So basically Pavel Pokhilko, who is my very talented postdoctoral fellow, Vibin Abraham and Gaurav Harsha, also my postdoctoral fellows, Ming Wen and Yu Ting Qiu, who are my graduate students, and these are my new adepts. And I would like to thank Qianan, who is my former student who worked on the tensor decomposition. And thank you for listening.
Thank you very much, Dominika, for your talk, and let's open the floor for discussions. Adam?
Yeah, thank you very much. So the basis set dependency, you have shown it is quite strong here. Do you have some super method to optimize the basis set for GW, or these are just standard procedures for atoms or something like that?
So basically, we optimize it for, it's like the standard procedure. So you basically optimize the coefficients, right? And the contraction coefficients and the exponents.
But then the threshold is Hartree-Fock energy, or what is the target?
So what is the optimization done against? So you optimize the energy, yeah? And you optimize usually, so we do the plane wave calculation, and you can optimize this versus the plane wave result in such a way that basically you try to mimic this, right? This unoccupied band in DFT, the best way. So that gives you some sort of starting point of this contraction coefficients and exponents. And that usually helps enough. We also penalize this for getting linearly dependent.
Okay. Thank you. And the second question is about the basis set superposition error. It is also known to be method dependent. How big is this? Have you tried to estimate it with S22? Is it comparable to something like a couplet cluster or
the basis set superposition error? So, to be honest, we use the supermolecular methods, right? So we evaluated the dimer energy, right? The monomer energy in the dimer basis. I don't remember how big was the difference.
Okay, thanks.
Okay, Matej?
For the Ising model or this Heisenberg chain, other than computational cost, is in this method in principle able to capture these dynamics, or you need to reduce it to this simpler model because it's unable to account for this?
To basically do, you mean the time dependent treatment?
Or the Néel temperature, like can you not solve, you have some spin-spin correlation in the two component treatment, right?
So we did, one can do basically what is called generalized Bain-Kadamov with GW. And we did work on that. It's expensive method. Like, there's nothing, nothing to hide here. But I don't think that this is the main problem in the field. Like the main problem in the field of this time-dependent method is that, even in the equilibrium, we not yet understand everything how to do it in solid, right? Or there are still some issues. And in this non-equilibrium, one of the biggest problem, right, is, for example, how do you describe the time-dependent kernel? You have two times, how do you time step, and so on. So that's, like, I would say, the time dependence of this ab-initio methods for solid, this is like absolute forefront, very expensive, and I'm not sure, like, if you wanted to basically do a simple spin dynamics, right, usually probably on a model system that would be fine. It's also not clear to me that the experiments in that field are so, far forward that you really need, right, like the fully ab-initio dynamics.
Arthur?
Yeah, very nice talk. I was wondering about these higher vertex corrections, whether there's a way to estimate their magnitude without having to fully evaluate these full integrals.
It's actually not that expensive because we use the decomposed integrals for the vertex, so it scales as n to the fourth, right? So like if regular GW scales as n to the third or n cubed, then this one scales n to the fourth. So I would say you can estimate it, like you can just do this calculation. One thing that, right, like there are also many flavors of this vertex. I mean, this community is amazing in producing misinformation, actually. So there are many flavors of this vertex, and you can do the cheap flavor, which would have this term like MP2, okay? Or you can do the full frequency dependent that vertex, but from the cheap one, you can estimate the magnitude.
And let's take the very last question of the conference from the chair himself.
Thank you. Thank you for the very nice talk. So you shown the Gaussians and plane waves, right? And yesterday we showed a very nice talk of Tomek Bednarek showing these Green's functions method for these feeder oscillations that looks like a B-splines. So would it be possible to implement B-splines?
Oh yeah. We can take probably any basis, right? So we have very active work on basically implementing other bases than Gaussians. Gaussians are actually quite insufficient, but the method is general, right? If you give us the integrals for anything, we can run it. So yes, I think we could. I would need to think about the details, but yes, I'm quite sure that we could do that.
Okay, so thank you very much. And with this, I think I will turn to the organizers who have some concluding remarks.
Yeah. Thank you, Mateusz. Thank you, Dominika.